Well, hello, pre-calculus students. Today's notes are on limits. And limits, this is a very exciting time for us because limits are the foundation for everything you do in calculus. So you're going to see limits a ton next year in calculus, and the more you understand them now, the easier it will be for you next year when you see limits. So let's just start with this notation right here. Let's just read this problem. This problem says find the limit as x approaches 2 of 3x minus 2. So this is right, the limit as x approaches 2 of 3x minus 2. Now, here's where thinking along calculus lines is different from thinking algebraically. In algebra class, what you would do is you'd say, when x equals 2, what does this equal? In calculus, you're saying, when x gets closer and closer to 2, what does the value of this expression get closer and closer to? And there's three ways to find a limit. One way is to find a limit graphically, one way is to find a limit using a table of values, and one way to find a limit is algebraically. So you'll notice I have my graphing calculator handy. Today we're going to find limits graphically and using a table of values, and tomorrow we're going to talk about how to find limits algebraically. Don't worry if you don't have a graphing calculator. Watch what you're seeing today, make sense of it, but tomorrow I'm going to show you how to do every single one of these problems without a graphing calculator. Okay, so this says find the limit of 3x minus 2 as x approaches 2. Here's what we do on our calculators. We say, let's graph this. So I'm going to press the y equals key. I'm going to type in there y equals 3x minus 2. Once we do that, we can press our graph key. And if you don't see your axes right in the middle, you might want to press your zoom key. In the 6th choice Z standard, we'll put those axes there. Once you have them there, you can just press the graph key every time. And you'll notice this is a line. No surprise, y equals 3x minus 2 is a line with y-intercept -2, slope of 3. On the top row of your calculator, there's a key that says trace. And when you press that, your cursor will trace along this line. And we can say to ourselves, when x gets closer and closer to 2, what does y get closer to? And it looks like when x gets closer and closer to 2, y is getting really, really close to 4. So I'm just going to put over here equals 4. So we're saying when x gets closer and closer to 2, y gets closer and closer to 4. So that's how we find a limit graphically. Here's how we can find a limit with a table of values. Well, you might know this, but above your window key up here, there's a menu that says Table Set. If you go to Table Set, let's start our table at 2 because that's where we're approaching. And the next thing we can type in here, the change of table, let's make that 0.01. I mean, our table is going to go up and down by 0.01. Now, above the graph key, you can press second graph, and it'll show you a table of values. And you will notice here with this table that as our x's get closer and closer to 2, our y's get closer and closer to 4. And it happens no matter if you go from the top or the bottom. So this verifies this answer that yes, when x gets closer to 2, y gets closer to 4. Okay, let's try another one of these. Okay, so now find the limit as x approaches -1 of this function, x squared plus x minus 6. So I'm going to press my y equals key. I'm going to clear what's there. I'm going to type in there x squared plus x minus 6. And let's graph that. And no surprise when you look at this graph, it's going to be a parabola because that x squared, it's going to be shifted down because of the -6. It's shifted a little more because of the x as well. But there's a look at our graph. Let's trace that graph. And as I get my cursor closer and closer to -1, it looks like my y value is getting closer and closer to -6. So I think maybe the answer is -6. Let's verify that answer with a table. So I'm going to go to my table set. I'm going to start at -1 because that's where I'm approaching. And if I take a look at my table of values, I'm going to scroll up a little so I can see that better. I can see that as x gets closer to -1, y is getting closer to -6. And it works from the top or from the bottom. Now, You might be saying to yourself, Mr. Ebert, this calculus stuff is easy, because if I would have just plugged -1 in here, I would have gotten -6. And on the previous example, if I would have just plugged 2 into here, I would have gotten 4. So what's this calculus all about anyways? Well, these first two examples are easier than anything you'll see in calculus, and you're 100% right. If you just plug those numbers in, you'd get your answer. But the vast majority of limits you see in calculus don't look like that. The vast majority looks something like this one. Oh my goodness, things suddenly got really tough. And here's the deal. If you plug 0 into the top, you get 0. If you plug 0 into the bottom, you get the square root of 1, which is 1, minus 1, which is 0. Now, 0 over 0, what is this equal to? Well, it's not equal to 0, which you'd think if you had that on top. It's not 1, the same number top and bottom, but it's not equal to that. 0 on bottom we know is undefined. This is this indeterminate number. We don't know what this is equal to. You see this a lot in calculus. We can't write that as an answer. That's not our final answer here. Let's find our limit graphically of this. Okay, so I'm going to grab my calculator again, and I'm going to type x divided by. Now, careful. All that stuff on bottom, I'm going to put in parentheses. Okay? Because we're dividing by everything. So divided by the square root of x plus 1. I'll get out of that square root sign, and I'll type minus 1. Close those parentheses. And let's take a look at a graph of this. I have no idea what this is going to look like. This is not so familiar. So there's our graph. It's kind of like a square root function. And I'm going to press my trace key. Now you'll notice when x equals 0, it doesn't give a value for y. That's because of this over here, because when we plugged in 0, this is impossible. But if I trace this and move my cursor left or right, I can see as x gets closer and closer to 0, it looks like y is getting closer and closer to 2. Okay, so this can't be our answer, but maybe our answer is 2. Let's verify that with our table. I'm going to set up the table. We'll start at 0 because that's where the limit's approaching. Let's go to that table. And notice it says when x equals 0, y equals error. But that's thinking algebraically. We don't care when x equals 0 what y equals. What we care is when x gets closer to 0, what does y get closer to? And it looks like when x gets closer to 0, y is getting closer to 2. So that table verifies this answer. All right, so what a limit is, it's saying when x gets closer and closer to some number, what does the value of this expression get closer and closer to? Let's take a look at another example. All right, fourth example here. Oh, this one looks really, really tough. Let's see what we can do. Well, if you just plug 1 into the top, you get 0. If you plug 1 into the bottom, you get 0. We know that's impossible. So let's let our calculator do our work for you. Now, careful. When you type something like this in your calculator, my number one suggestion is put the entire top in parentheses, put the entire bottom in parentheses, because it's everything up here divided by everything down here. So I'm going to press y equals, clear what's there. And in parentheses, we can type in there x to the third power, which means this caret key to the third power. Make sure you get out of that power. Minus x squared plus x minus 1. If we close those parentheses and divide by, in parentheses once again, x minus 1. Now, if you're doing one of these and you check your key or something doesn't quite work, I'm guessing it's because you forgot those parentheses. But let's graph this. And you might be surprised at the shape of this graph. It's actually going to be a parabola. It actually makes sense that it's a parabola because we're taking x cubed divided by x, which gives us x squared. So we've got this parabola. And I'm going to press my trace key. And if I trace that function, when x gets closer and closer to 1, it looks like y is getting closer and closer to 2. So I think the answer might be 2. Let's verify that with a table. Let's set up our table so that it starts at 1. Remember, because this x is approaching 1. Let's go to our table. Notice, kind of cool, when x equals 1, there's an error, but we don't care. We don't want to know what y is when x equals 1. We want to know what is y getting closer to when x is getting closer to 1. And we can say that, hey, this is happening from both sides. It looks like it's getting closer to 2. I think that verifies our answer. All right, hopefully at this time you're thinking, okay, limits aren't so bad. As long as we have that calculator handy, we can trace our graphs to find a limit. We can look at a table to find a limit. Let's take a look at a little trickier function. Okay, now this kind of function here, this is what's called a piecewise function. We saw these at the start of the year, and you're going to see these a lot next year. Okay, so this is saying find the limit as x approaches 3 of the function where this is the function. And I just put it down here because I was running out of room to type up here, so I just put it down here. Typically, you see this all on one line, okay? So here's what this is saying. It's saying the function is equal to 2 for all x values not equal to 3. And the function is equal to 0 when x equals 3. Now, to be honest with you, these piecewise functions are much easier to graph by hand than they are on our calculator. So I'm going to sketch a really rough set of axes. And I'd ask you to do the same, please. If we wanted this to be totally accurate, we'd pull out some graph paper. But I don't know about you, but I don't have much graph paper laying around at home. So I'm just going to try to graph this by hand. So here's what this is saying. It's saying y equals 2. That's this, f of x equals 2. As long as your x doesn't equal 3. So y equals 2 is a horizontal line through the y-axis at 2. And we're going to draw this line that goes straight across here through the y-axis at 2. Except right here, see this point right here? We're not going to have this line because when x does not equal 3, we can draw the line. When x does equal 3, we can't. So I'm going to put an open circle at that point and draw a horizontal line through the y-axis at 2. Now this is saying y equals 0. But y equals 0 only at one point. Y equals 0 only when x equals 3. So when x equals 3, y equals 0. That's just this one point here. So this is kind of a weird graph. So when y equals 3, x equals 0. But for every other value, x equals 2. Okay, so let's just think about how the limits work. This is saying when x gets closer and closer to 3, what's the value of the function? So when x gets closer and closer to 3, well, the value of the function is 2. The value of y is 2. When x gets closer and closer to 3, the value of y is 2. Now, when x does equal 3, the value of y is 0. But to be honest, we don't care. That's thinking algebraically. We don't want to think algebraically. We don't want to say, when x equals 3, what does y equal? That's this number. We want to say, when x gets closer to 3, what does y get closer to? Well, y is just staying. Y is equal to 2 for all these points here. You can be infinitely close to 3, x value 3, the y is still equal to 2. So this answer, this limit, is equal to 2. And we have to think differently. It's a different mindset. When you think algebraically, you might say, I don't get this. When x equals 3, y equals 0. But don't think when x equals 3. Think when x gets infinitely close to 3, y is still equal to 2. So there's that answer. All right, we'll see more of these down the road. Let's continue. Okay, we're going to pull our calculators back out for this one. So we want to find this limit, whoops, as x approaches 0 of this function. Okay, so let's grab our calculator. Let's clear what's there. Now this is the absolute value of x over x. Absolute value, your calculator does have it. It's in the math menu. So if you press math and you go over to number, it says abs. That's not talking about your rock hard abs, ladies and gentlemen. That's absolute value. So let's use absolute value of x. We'll get out of the absolute value sign divided by x. And we've never graphed anything like this before, so this is going to be a little bit of a surprise. Let's take a look at what this is. So if I graph this, oh, it's just a horizontal line. That's weird. Oh, but then it jumps up. So we've got this weird graph that comes across and then jumps up and then goes over here. Okay, so let's trace this. We're saying when x approaches 0, what does y equal? Well, you notice here that when x gets closer and closer to 0, y is always equal to -1. So it looks like this answer might be -1. But then if you look on the other half of the graph, when x gets closer and closer to 0, y is always equal to 1. Well, that's weird. We have these two different answers. Which one is it? I'm going to look at a table of values. We used a table to verify things before, so let's see if our table will clear things up this time. Okay, so interesting, right in the middle of that table, it says when x equals 0, y does not exist. There's an error there. But take a look. When x gets closer and closer to 0 from the one side, y is always equal to -1. When x gets closer and closer to 0 from the other side, y is always equal to 1. Well, for a limit to be possible, this must approach the same value from both sides. So here's what we say in this case. We say, hey, we're approaching two different values. This can't be, we can't have this. So what we say is that the limit does not exist. And the cool way to write that, if you write it all out in words, you don't look very smart. If you write DNE, that means the limit does not exist. If you've ever heard that before, get on Netflix, see if you can find Mean Girls, see if you can watch that movie. It's a classic. Well, not really a classic, but there's a scene at the end of it where the hero of the story shouts out in the math competition, the limit does not exist. If I was in class with you right now, we would watch that clip. We would laugh at that clip. We would make sense of that clip. But for now, you just have to trust me. So a limit does not exist when it approaches two different values, one value from the left and one value from the right. All right, I have two more examples to show you. Thanks for bearing with me. Let's take a look at our last two examples. Second to last example, let's find this limit, and let's graph this one as well. Okay, so I'm going to type in here 1 divided by x, use my caret key, to the 4th power. And I'll graph that. Let's take a look what this looks like. Ooh, that's kind of a cool graph. Haven't seen that a whole lot. But if we trace that graph, we can see that, well, as x gets closer and closer to 0, y just gets bigger and bigger. It's getting infinitely big. And if I pass 0 and I go from the other side, same thing happens. So it looks like as x gets closer and closer to 0, this gets closer and closer to infinity. Well, that's kind of weird. We can't, you know, what a limit is, it's saying when x gets closer to a number, what value does this function get closer and closer to? If our function approaches infinity, we stop right there and we say, hey, in this case, the limit does not exist either. So now we have two different situations where a limit does not exist. If your function approaches two different numbers, one from the left, one from the right, and your function, or I should say, or if your function approaches some infinitely big or infinitely small value, we say the limit does not exist. Now there's one more case where the limit doesn't exist, and that's this last function. So let's just graph this. Let's take a look at one last limit, and then we'll put our notes aside. Okay, so y equals, I'm going to graph the limit. Well, let's just graph y equals the cosine of 1 divided by x. And one thing when you do this, make sure your calculator's in radian mode. In fact, all next year in calculus, your calculator's going to be in radian mode for everything. And it's really hard to see what's going on here. I'm just going to zoom in. You don't necessarily have to. You can keep that window where you want it. But if you take a look at the graph I've got here where I'm zoomed in, you'll notice that the graph gets more and more variable as x gets closer to 0. If I trace my graph, I can see that, well, if I try to trace this thing, okay, it looks like as x gets closer to 0, y approaches something, but then it jumps up and down quite a bit. And if I look at a table of values, I notice the same thing happens. So what's going on with this, it's a really weird function. the closer x gets to 0, the more the graph just varies, the more it jumps around. So what's happening, like to make a really rough sketch of this, is that this is slowly getting close to 0, but as it gets closer, the graph goes up and down. As it gets closer and closer, it gets up and down more and more, and then it just slowly kind of does this again. So the closer this function gets to 0, the less this gets to approaching anything. So this just goes up and down so fast you can't tell what it approaches. So once again, you say the limit does not exist. So there's 3 cases where it doesn't exist. 1, if your graph approaches 2 different values, one from the left, one from the right. 2, if your graph gets infinitely big or infinitely small. And 3, if there's just infinite variation. It goes up and down so fast and you can't tell what it approaches. Now, I will tell you, the vast majority of limits you will ever calculate do approach a number. Most of the problems you're going to see on your homework, on your practice, on your test, do approach a number. But if you ever get something where one of those cases occur, we can say the limit does not exist. All right. Hopefully that made some sense to you. If not, please check in with us. We'll gladly help you out. And the next set of notes on 11.2 is going to show you how to do every single one of those without a graphing calculator. Okay, take care, everyone, and I hope to see you soon.